everyone, and welcome back. In this video, we're going to continue our exploration of simple linear regression, and we're going to be coming back to the realm of hypothesis testing and focus on comparisons of linear regression parameters. We've already done hypothesis testing on single linear regression parameters, for example, beta 1 hat, beta 0 hat, and rho, but now we're going to be comparing two bivariate sets and their linear regression models and seeing if there's a significant difference between the models themselves and also the parameters individually. So let's just look at a couple things that we need to understand first off, right? So let's assume we have one linear regression line, let's call it y hat 1, and this is going to be equal to beta hat 1, 1, x plus beta hat 0, 1. So it's going to be the predicted value for the first set is equal to the slope of the first set plus the intercept of the first set. And then we're going to have another line, which is going to be generated from a bivariate data set, and it's going to have a slope for that second set, and then an intercept for that second set. Right? So let's look at the graphical interpretations of these lines and the various circumstances that we may encounter. So case 1 is where we have, let's assume this is line 1. So let's assume this is line 1 and line 2. And let's assume this is line 2. Right? So notice that this is the vertical intercept beta 0 hat for both of them, and they are equal. So what can we say? So clearly, at least from this picture, we see that beta hat 1, 1 and beta hat 1, 2 are not equal to each other, i.e. they have different slopes, but the vertical intercept for one and the vertical intercept of the second are equal to each other. Another scenario that we could encounter is, let's assume we have this line and that line. So let's assume that's line 1, line 2, or vice versa, it doesn't really matter. So here the slopes, beta hat 1 for 1 and beta hat 1 for 2 are equal to each other, but they have different vertical intercepts. So beta hat 0 for 1 and beta hat 0 for 2 are not equal to each other. So when we test whether or not the slopes are equal to each other, what we're pretty much testing for is parallelism. Because if the slopes are equal to each other, that means these lines are parallel to one another, at least in the two-dimensional sense. So another scenario that we could encounter, let's assume we have this curve. Let's keep constant with the color. Actually, let's change the colors up a bit. Let's do purple. So let's assume we have that curve. Let's assume we have that curve. So notice here that the slopes are not equal to each other and the vertical intercepts are not equal to each other. So beta hat 1 of the first and beta hat 1 for the second are not equal to each other. And beta hat 0 for the first and beta hat 0 for the second are not equal to each other. And then, what other case are we missing? Take a guess. So again, that's line 1, line 2. Here I'm just going to draw, or it looks like I'm drawing only one line, but actually they're on top of each other. So what does it mean to be on top of each other in sense of lines and their parameters? Well, clearly they have the same exact slope. Beta hat 1, 1, and beta hat 1 of 2 are equal to each other, and beta hat 0 of 1 and beta hat 0 of the second are also equal to each other. So when we test whether or not both of these parameters are equal to each other, what we're pretty much testing for is coinciding, or that these lines are coinciding with one another. Yeah, let's just coincide. Yeah, let's call it coinciding lines. Some people call it the test for coincidence. Coincidence. Test for coincidence. That is, they are equal to one another in both parameters of the structure. So let's first off focus on the beta 1s. So is there a significant difference between the slopes of these lines? So let's briefly talk about the interpretations of these parameters. So remember, beta hat 1 for either the first or the second sort of corresponds to the rate of change of the data points or the predicted values as you proceed along the control variable domain. So the larger the slope in terms of positives, the faster it grows in the positive direction. And in terms of beta 0 hat, that can be interpreted in terms of the initial condition. So when x is equal to 0, where do you sort of start with in terms of everything? And that's definitely appropriate if the control variable is time. But usually we don't use time as the control variable in the simple linear regression because that's a whole entire different world of analysis, which we'll eventually get to. But rate of change and initial conditions are good starting points for general or generalized interpretations of these linear regression parameters. So let's start off by focusing on if there's a significant difference between the rates of change for these linear regression parameters. Let's first recall a standard error formula that we derived in the single bivariate linear regression analysis discussion. So the standard error for a single line slope is going to be equal to 1 over Sx times the square root of the error sum of squares divided by n minus 2 times n minus 1. As I've already repeated a few times, you can technically rewrite this in another way. You can write this as 1 over Sx times the square root of the error sum of squares divided by n minus 2 times 1 over the square root of n minus 1. Because this term underneath this first radical, that's precisely equal to the mean square error of our error term. So of course the square root of the mean square error, that would be an approximation for the standard deviation for each of those normally distributed random variables that we talked about in our assumptions, right? So that distribution should be normal, should have some standard deviation, it should be equal to sigma, regardless of the distribution that you choose, right? That should not change. So of course you can write that in a more compact way. So the standard error for beta hat 1 is going to be equal to, we can write that as sigma all over Sx times the square root of n minus 1. And of course that's equivalent to saying that the variance of the random variable beta hat 1 is equal to sigma squared all over Sx squared times n minus 1. All right, so now let us take a look at the comparison version of these structures, right? So how are we going to do that? So we first need a null hypothesis to test. So our test is going to be that the slopes of each of these regression lines are equal to each other. So how are we going to go about this? So you probably can guess already. We're going to define beta 1d to be the difference in the slope of the first and the slope of the second. You can subtract them in any direction. You should get an equivalent result as long as it's a two-tailed test. So if we define that to be equal to so, that means this null hypothesis is equivalent to saying that the difference between them is equal to 0, and we should already know how to test that via the single bivariate test approach, right? So if that is the case, well, we need a point estimate for beta 1d. So you should be able to prove that the expected value for beta hat 1d actually is equal to beta 1d. So that's a very easy proof to go through. It's practically the same exact proof as we have done for all the other differences in parameters such as proportions and means. So what about the variance for this particular random variable? Now that's usually the tricky part, right? Now it's very important to note that these samples S1 and S2 should be independent. If they're not independent, of course the math gets extremely messy. We're not going to be considering that dependent case, so let's just assume they're dependent just to make things easy, just for now. So what is the variance of that random variable? So the variance of the difference in slopes is going to be equal to the variance of beta hat 1, 1 minus beta hat 1, 2. That's the point estimate for the difference in population slopes. If they're independent, we can distribute that over, change the minus to a plus, and that's going to give us the variance of beta hat 1, 1 plus the variance of beta hat 1, 2. And we should already have formulas for those. That's going to give us what? So the variance of beta hat 1d is going to be equal to, so sigma 1 squared over sx1 squared times n1 minus 1 plus sigma 2 squared all over sx2 squared times n2 minus 1. All right, so notice I have two different sigmas here. I have sigma 1 and sigma 2. So keep in mind these distributions that we're sampling from one population that's bivariate and another from another bivariate distribution, there's no requirement that these distributions, these normal distributions, have the same exact variance. As long as those purple distributions have the same variance, as long as these green distributions have the same variance, then the assumptions for the individual linear models is met. Now, of course, if purple sigma and green sigma are equal to each other, yes, the math gets extremely easy, but it's not required that they both be homoscedastic in terms of their y variance. That's not a requirement for comparisons. It just makes things sometimes easier. So that's the numerators of each of these terms. The bottoms are, of course, the variance of the sample covariate terms. And of course, those are the sample sizes minus 1 or the univariate degrees of freedom. So if that is my variance, what is my standard error? So my standard error for beta hat 1d, or the difference in slopes, is just going to be equal to the square root of sigma 1 squared all over sx1 squared times m1 minus 1 plus sigma 2 squared all over sx2 squared times n2 minus 1. And that's the standard error formula for the difference in slopes. Now, of course, you should be assuming that each of these distributions are normally distributed, so we will be using a t-distribution in all of these hypothesis tests with a degrees of freedom equal to m1 plus n2 minus 4, but we'll get into that in just a moment. But before we get into that, I just want to mention some basic simplifications that could occur if you know a bit of extra information about these populations that you're sampling from. So firstly, we don't usually know what these sigmas actually are equal to each other. So we usually have to approximate them with something, right? So of course, let's assume that we're going to approximate sigma 1 squared. We're going to be approximating that with s1 squared, which is equal to the mean square error of the first bivariate data set. And let's assume sigma 2 squared also is not known. We're going to be approximating that with s2 squared, where s2 squared is the mean square error for our second bivariate sample. And let's also assume that we have evidence to believe that sigma 1 squared and sigma 2 squared are equal to each other, in particular that they are equal to some sigma squared, but we do not know what that sigma is, because if we knew what sigma was, then we wouldn't have to approximate it, right? So if that's the case, notice that these sigma squares are now equal to each other, and we can factor that out of the square root. So only under those assumptions, we can say that the standard error for beta 1 hat d is going to be equal to sigma times 1 over sx1 squared times m1 minus 1, and then plus 1 over sx2 squared times n2 minus 1, right? So if we do not know what the sigma is, that means we need to approximate it. So similar to the proportions, we can approximate this with a pooled variance, right? So we can pool together s1 squared and s2 squared because we're approximating the same exact variance, right? So we can write the pooled variance to be equal to n1 minus 2 times s1 squared plus n2 minus 2 s2 squared. So those are the degrees of freedom in the bivariate sense. That's why it's minus 2, not minus 1. And then on the bottom, it's going to be n1 plus n2 minus 4. Right? Because it's n1 minus 2, n2 minus 2, so it's n1 plus n2 minus 4. So if that's the case, that means our standard error under these assumptions is going to be equal to beta 1d hat is going to be approximately equal to the pooled standard deviation of each of them, because remember, we're assuming that these distributions in purple and green are equal to each other, so that's the assumption we're working with. And then that's going to be 1 over sx1 squared times m1 minus 1, and then plus 1 over sx2 squared times n2 minus 1. And that's that simplification that you can have if you believe that the response variable for both bivariate populations are homoscedastic to one another, right? So that's actually pretty easy. Also notice we can make this more simpler if we know another assumption. Now this also is not very realistic, but let's also assume that sigma x1 squared and sigma x2 are both equal to each other, and let's assume that those are both equal to, let's call it sigma x squared, right? So that is what these things are approximating, right? So usually we do not know what that is equal to, so that's approximately equal to, say, some number sx squared. So how are we going to approximate sx squared? So if that is the case, then our standard error for beta hat 1d would be approximately equal to, so sp all over sx times the square root of 1 over, actually let's write it 1 over sigma x, right, because that's technically what we're approximating first. Then we're going to have n1 minus 1 plus 1 over n2 minus 1. All right, so nice little radicand there. And now we need to approximate sigma x with something. So what are we going to approximate a univariate variance with? So we're going to approximate that with a pooled variance as well. So that's going to be the pooled variance of a univariate. So that's going to be n1 minus 1 s1 squared plus n2 minus 1 times s2 squared all over n1 plus n2 minus 2. So this formula is the same as the pooled variance formula. Do you remember for which test? That's for the difference of means, the pooled variance approach. That is, if we have evidence to believe or we know that the populations are homoscedastic to one another, we can pull them together, right? So if that is the case, that means our standard error formula for the differences in slopes can be approximated simply by the approximation for the response variable standard deviation, and then over the pooled variance for the control variable variance that are homoscedastic to one another also, and then times the square root of 1 over n1 minus 1 plus 1 over n2 minus 1. And that is probably the most simplest you can get it with those two extreme assumptions, right? And that is how we do the standard error for the difference in slopes. So now what about the confidence interval? So for the confidence interval, you need a critical value. So that's of course going to be a t critical value with the degrees of freedom equal to m1 plus n2 minus 4 because we're comparing two bivariate populations. And we're going to have a test statistic just in case you want to approach this from p-values. So the test statistic is going to be equal to the difference in slopes minus the claimed value of the difference in parameters, which is usually assumed to be 0, but it's not necessarily equal to 0, but you can choose it to be 0 or not equal to 0, depending if you want, so it's a little bit more flexible. And of course, that's going to be divided by the standard error associated to this point estimate. And again, that's going to be compared to a t-distribution with that particular degrees of freedom in case you're interested in calculating your p-values. So that is how you do hypothesis testing. So again, what are we actually testing for in this particular world? So again, the null hypothesis for these was beta 1,1 equals beta 1,2. So this is often referred to as a test for parallelism. That is, if the slopes are equal to each other, they are parallel to one another in the two-dimensional sense. Now that we have all of the hypothesis testing done for the slope, or the difference in slopes for the linear regression lines, now let us focus on the intercept and difference between these linear regression lines. So for the difference in intercepts between two linear regression lines, we of course need to recall the single bivariate intercept formula and its standard error. So remember that that's going to be equal to the standard error of beta hat 0 is going to be equal to the square root of the error sum of squares divided by n minus 2 times the square root of 1 over n plus x bar squared all over sx squared times n minus 1. All right, so that's the standard error for the intercept, and if you square that, that gives you the variance of beta hat 0. Keep in mind that is equal to sigma for the response variable, so you could write it in that form if you want. So what is the null hypothesis that we're going to be looking at this time? So now we're going to see if there's a significant difference between the intercepts of these linear regression lines. So that's going to be equal to beta 0 of the first and beta 0 for the second. So we're going to define beta 0 difference to be equal to beta 0 of the first minus beta 0 of the second. So that means this null hypothesis is going to be equivalent to beta 0 difference is equal to 0. And then we can pretty much move that into the single bivariate analysis, and practically nothing much will change. So we can show via the same exact approach, so we're going to take the variance of that random variable. Let's assume that these two samples are independent again, else the math of course gets extremely difficult because you have to include variance terms since they're dependent to each other, and covariance can definitely be very tricky because we have to have a joint distribution to model that covariance usually. So if they are independent, then you should be able to show that the variance or the standard error for the difference of vertical intercepts is going to be equal to what? So let's use the sigma perspective. So we're going to have a big square root with a bunch of stuff underneath it. So we're going to have sigma 1 squared times 1 over n1 plus x bar 1 squared all over sx1 squared times n1 minus 1, and then plus sigma 2 squared times 1 over n2 plus x bar 2 squared all over sx2 squared times n2 minus 1. And that is the beautiful standard error for the difference in vertical intercepts. Now, some simplifications can be done if you assume some things about the populations. For example, if sigma 1 squared equals sigma 2 squared is equal to sigma, and let's assume that we're going to be approximating that with a pooled standard deviation, similar to how we did for the difference in slopes for the two different regression lines. Then, if that is the case, that means we can drastically simplify this to be the standard error of beta hat 0d is going to be equal to, so this and that can factor out, that becomes just sigma, and that's going to be approximated by SP, so this is going to be approximation, so it's going to be SP times 1 over n1 plus 1 over n2, and then plus x bar 1 squared all over sx1 squared times n minus 1, and then x bar 2 squared divided by sx2 squared times n2 minus 1. Right? And that is the simplification that you can do. Now, even if the control variables have the same exact variance, yes, you can probably factor it out of these first two terms, but that's not really going to make a lot of things easier because we still have these 1 over n1s plus 1 over n2s to deal with, and usually those samples aren't even equal to each other, so there's not much else you can really do in theory to make this equation a lot more simpler. There are special cases, but we're not going to get into the very special cases. So that is our standard error formula that can take, either that form or the more general term that preceded it. So we're going to be using a test statistic that's going to follow a t-distribution. And why is that? Well, we're sampling from two bivariate normal distributions, so everything should be associated to a t-distribution because we're just dealing with a bunch of normal random variables. For example, beta 1 is a normal random variable, beta 0 is a normal random variable, just everything is a normal random variable, at least theoretically. Right, so the first thing that we're going to be using is our point estimate, beta hat 0d, and then we're going to be comparing that to the claimed value of the difference, which is typically assumed to be 0, but it doesn't have to be. And that's going to be divided by the standard error of that point estimate, beta hat 0d. And again, the degrees of freedom for this t-distribution is going to be n1 plus n2 minus 4, because we're looking at two bivariate distributions, so n1 minus 2 plus n2 minus 2. And that is how to do tests for the equality or difference between the vertical intercepts of simple linear regression models. So now that we've talked about the test in difference in slopes and the test in difference for intercepts, now let us talk about the test for coincidence. So what is the test for coincidence and what does it mean for two lines to be coincident? So again, that means that these two lines, L1 and L2, are exactly on top of each other. That means their slopes are equal to each other and their vertical intercepts are equal to each other simultaneously. So if we fail to reject 1, the null hypothesis that the slopes are equal to each other, so beta 1, 1 and beta 1, 2, that means we have evidence to believe that they are equal to each other, and H0, beta 0, 1 and beta 0, 2 are equal to each other. That is, we have evidence to believe that the vertical intercepts are equal to each other. That means we have evidence to believe that these lines are one and the same, right? So that is these two lines. So what were these two lines equal to each other? Well, what were these two lines individually? So remember that's y hat 1 is equal to beta hat 1, 1, x plus beta hat 0, 1. And y hat 2 is equal to beta hat 1, 2, x plus beta hat 0, 2. So if these two lines are equal to each other, we should be able to combine them into a single line. In particular, y hat is equal to beta hat 1x plus beta 0 hat, right? So we have these two slopes, beta hat 1, 1 and beta hat 1, 2. We need to be able to use them to approximate that value, beta hat 1. Also, we have beta hat 0, 1 and beta hat 0, 2, and we need to use both of them in order to get an approximation for beta hat 0. So how are we going to do that? So an approximation for beta 1 hat is sort of like a pooled slope formula. So that's going to be approximately equal to each other, n1 minus 1 times sx1 squared beta hat 1, 1 plus n2 minus 1 times sx2 squared times beta hat 1, 2 all over n1 minus 1 sx1 squared plus n2 minus 1 sx2 squared. Right? So we're weighing these slopes with respect to both their sample sizes and also their variances. Now, why is that? Because if these two are going to be pulled into the same exact realm, then that is going to have a single variance, right? So if these two do not have the same exact variance for those response variables, then the variance of this newly created linear regression line is going to be a combination of those two, right? But notice in this formula, what if they are equal to each other? So notice if these variances, because remember, this is an approximation for sigma x1, that's going to be an approximation for sigma x2. Same thing for those, I mean sigma x squared for each of them, right? So if sigma x1 squared equals sigma x2 squared, if those two are equal to each other, then a better approximation for this is just going to be equal to n1 minus 1 times beta hat 1, 1 plus n2 minus 1 beta hat 1, 2 all divided by n1 plus n2 minus 2, right? And why is that? Because notice that if we factor out a sigma squared at the top and sigma squared at the bottom, they're going to cancel to each other because they're equal to one another. Isn't that beautiful, right? So that is only true if the response variables are homoscedastic with respect to one another. If they're not, you have to use this more general term. Also, what about the beta zeros? So one can show that beta hat 0 can be approximated by n1 beta hat 0, 1 plus n2 times beta hat 0, 2 all over n1 plus n2. Now remember, or notice, that it's not n1 minus 1 and n2 minus 1, and the bottom isn't n1 plus n2 minus 2. And why is that? I'll leave it to you to sort of think about. But for now, I'll just leave it there. So those are the approximations for those newly created linear regression lines if we have evidence to believe that the slopes and also the vertical intercepts of the separate linear regression lines are both equal to one another. Now that we have looked at each of the four cases for our comparisons of linear regression models, now let us look at how to compare their correlation coefficients. So the null hypothesis in terms of equal coefficients is going to be equal to rho 1 is equal to rho 2, and let's assume that we're going to be working with a two-sided alternative. Now remember the Fisher transform for correlation coefficient. Remember that the Fisher transform is going to be represented by zeta rho is defined to be equal to the inverse hyperbolic tangent of rho. Okay, so that means this is true if and only if the null hypothesis zeta rho 1 and zeta rho 2 is also true. So they're true if and only if the other is true. Okay? So we're going to be approximating the confidence interval via the Fisher transform, and the test statistics and p-values will follow a test statistic that's followed by a t-distribution as usual. So let's start off with the confidence interval approach, but this is going to follow a similar pattern, just like the single bivariate correlation test via the Fisher transform. So we're going to define zeta r1 to be equal to the inverse hyperbolic tangent of the first correlation coefficient. So that's the correlation coefficient for the first bivariate data set. And then we're going to have zeta r2, which is going to be equal to the inverse hyperbolic tangent of the second correlation coefficient. And then we're going to be looking at the difference, so zeta rd, the difference in zeta r1 and zeta r2. You could also do zeta r2 minus zeta r1. Okay? So notice that this hypothesis is true if and only if what? If and only if their difference, zeta rho d, is equal to 0. So that's what we're pretty much working with, and that's why we're using this as a point estimate for that transformed parameter. Right? So what is the standard error for single Fisher transform? So let's just recall that in case you don't already know. So the standard error for the Fisher transform of a single bivariate sample estimate is going to be equal to 1 divided by the square root of m minus 3. Now remember, this is heavily dependent on extremely large sample sizes and bivariate normality of the sample that we are sampling from. So if that is the standard error of zeta r, you may want to pause this video and take a guess. What would the standard error of the difference in correlation coefficients, in particular that variable, be? Let's assume again that these two populations are independent of one another. So what would that standard error be? So that's going to be equal to the square root of 1 over n1 minus 3 plus 1 over n2 minus 3. So this requires that both of these distributions, these bivariate distributions, are bivariate normal, and n1 and n2 are both extremely large. So once you have that, then we have a margin of error. So a margin of error for a confidence interval for zeta r is going to be equal to a z critical value, so no degrees of freedom needed, times the standard error of zeta r d. Right? So then we can construct a confidence interval for zeta rho d. That's going to be equal to zeta rd minus epsilon, and then zeta rd plus epsilon. And then we can get our confidence interval for rho d, the difference in correlation coefficients, to be equal to, let's write these in brackets because we're going to have parentheses inside these brackets. That's going to be equal to the hyperbolic tangent of zeta rd minus epsilon, so the hyperbolic tangent of the lower bound of the previous interval, and the hyperbolic tangent of the upper bound, zeta rd plus epsilon. So that's our confidence interval for the difference in rho d, and remember we're comparing rho d, or the difference in correlation coefficients, to be equal to 0, right? So if 0 is in there, that means we have evidence to believe that they're approximately equal to each other. Okay, so that is the confidence interval approach for these particular things. And what about the test statistic? So since we're using a z distribution, we're going to be having a z test statistic, and that's going to be equal to, let's do Let's see, what is it going to be equal to? Let's think about it. So if you remember, if we approach things from the test statistic perspective, we're actually not going to be using a z distribution, we're going to be using a t distribution. We have some estimations that are going on if we're going to apply directly r as an approximation for rho, right? So how are we going to go about that? So if we're interested in doing, for example, rho 1 is equal to rho 2, then we have to define, for example, rho d to be equal to rho 1 minus rho 2. Right? So that will turn this hypothesis into rho d is equal to 0, and that means we need to approximate rho d with rd. And one should be able to show that the expected value of rd actually equals to rho d. That means it's an unbiased estimator for that particular parameter. Let's recall also the standard error for r, just r itself, just a single bivariate sample. So the standard error associated to r is going to be equal to the square root of 1 minus r squared divided by n minus 2. So if that's the case, what is the standard error associated to the difference in r's, right? So remember, rd is going to be equal to r1 minus r2, and again, let's assume that these two are independent of one another. So that's going to be equal to the square roots of 1 minus r1 squared all over n1 minus 2, and then plus 1 minus r2 squared all over n2 minus 2. Once we have our standard error, then everything else should follow very, very nicely. So we're going to have a test statistic, a t-stat, going to be equal to the point estimate minus the claimed value of the difference divided by the standard error of RD. Again, this is typically taken to be 0, but it doesn't need to be. Since we're working with the t-distribution, we also need a degrees of freedom, so what should that be? So if you remember, for the single bivariate test for the correlation coefficient for the t-test approach, it was n minus 2 degrees of freedom for just the single bivariate approach. So what would the degrees of freedom for this be? So the degrees of freedom, again, would be n1 plus n2 minus 4, right? And that is how you can do hypothesis testing for the correlation coefficient, the difference of the parameters, the slope and the vertical intercept, for two simple linear regression models. So up to this point, we have discussed several different concepts associated to simple linear regression. In particular, we should be able to do hypothesis tests for values of our simple linear regression parameters, beta 1 hat, beta 0 hat, and rho. And also we should be able to compare individually the parameters of two simple linear regression lines, beta 1 1, beta 1 2, beta 0 1, beta 0 2, rho 1, and rho 2. Also, for a single simple linear regression line, you should be able to construct confidence intervals and prediction intervals for practically any value for which you are interested in predicting. So up to that point, those are all of the foundations, including the theory and assumptions for simple linear regression. Next, we're going to be looking at how to extend this to higher dimensions. That is more than one independent variable. So I hope to see you there. Take care.